Okay, so I'm back, and in this video, I'm going to be starting a series, which is going to be mainly more educational, I guess. It's just, this is mainly for like people doing like comp sci or computer engineering, electrical engineering, and things of that nature, and it's going to be an introduction to digital systems design. Um, so yeah, so I guess to start off, I'll go over like the the initial topics that I know that I want to go over in this series. Um, so what we are going to definitely be covering, um, let me bring this down, are like what exactly are digital systems, number systems, and like different types of conversions between them, binary codes, Boolean algebra, logic gates, gate minimalization, and combinational logic. So I guess we'll just jump right in. And this is going to be the intro to like what digital systems are. So they are systems that store information in a discrete way. Um, by that I mean like they're either on or off, they're one or zero. Um, there's only two specific values that any type of information can have. Um, and so yeah, that's typically with a one or a zero. So whether or not there's a signal running through a particular point dictates whether or not it's a one or zero. So if there is a signal, then it's a one. If there is no signal, then it's a zero. Um, and this is also translated into like on or off, and there are several other terminologies like set and clear, um, but you get the point. It's like two different possible discrete values when you're talking about digital systems of this nature. There's also analog systems, but that's a whole different thing. That basically means you have a large range of different possible voltage values, and that's just not what digital systems are. Digital systems have two distinct values, um, and that's what the focus of this series is going to be. So I just also wanted to talk about a couple of the different examples that are fairly common because digital systems are very commonly used in our lives and we pretty much use them all the time. So we have telephones, we have TVs, we have cameras and computers. These are some simple examples that we have. Um, and yeah, so I just wanted to give you an idea of what is out there that could possibly be a digital system. So from here, I want to transition to things that are actually going to be important foundationally if you want to learn more about this topic. So what we're going to start off with are number bases. So for example, all of math pretty much that you've learned throughout high school is conducted in digits which are 0 to 9. So, for example, like if you have the number 4,733, um, you have a base of 10 in this number. So, for our purposes, we'll mainly be writing them with a notation of 10 here to just so you know exactly what base we're talking about, at least for this video. Later on, we'll mainly be working in binaries, so we usually won't need to write a distinct number there, so because you'll just assume that it's in binary. But for now, just to get a feel for what I'm talking about here, what you have is for as you know, like this is the ones place, tens place, hundreds place, and thousands place. Um, this is just something you'd probably know by going to high school and like learning about math over the course of as many years as you have. So, but there is another way of writing this. So what you have is this is 10 to the 0th place. Then you have 10 to the first, 10 to the second, and 10 to the third. And this will go on like this way, uh, all the way down to 10 to the infinity. Um, so yeah, decimal points, they're not really important for our purposes because you usually don't have a you don't really have decimal binary or any of the other number systems that we'll go with. Technically, you can have them, but it's just not really commonly used. Usually, if you want something to be um, to be sensitive to certain decimal points. So if you want it to go down to like 0.01 as your sensitivity for a certain system that you're trying to make, what you'll do is you'll just treat it as, for example, 4733 and then 0, 1. You won't really deal with the decimal point, and it's just that your system will deal with it a little bit differently as opposed to actually having to deal with that decimal. So it's just really not common for you to care about that. Um, and so just to show what I mean by this, like this area here, I do have a breakdown of 4,733 and how that's written with this notation. So what you have is 4 times 10 to the third, which means it's 4,000, and then you add 700 to it, which is 7 times 10 to the second. Then you have 3 times 10 to the first and 3 times 10 to the zeroth. Um, so as you probably know, this is 1,000, this is 100, this is 10, and this is 1. So this is sort of the basis of how these different number systems work. Because you have a base of 10, every single digit as you move further up along the line starts with that base to the zeroth, then the first, second, third, and so on. So this was just an easy way for me to sort of show you guys what I'm talking about um, with a base of 10, because everyone for the most part knows and understands base 10 notation, even though you might not have known that it was called base 10 or may not have even realized that it was base 10 because you're just so used to using it. You don't really think about it as base 10, but that is what it is. So from there, I do want to talk about some of the common bases that we'll be using. To start off with, we have hexadecimal. So this is a base of 16. So what this means is that we have 16 different possible values for each digit. So as you're probably thinking, how can we have that when we only have numbers 0 to 9 for each digit? So what we actually do for this is we have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So these are our first 10 values. Then we go on and do A, B, C, D, E, and F. So it's 9, 10, 11, 12, 13, 14, 15. So we have a total of 16 possible values, 0 to 15. So it's 0 to 15. And that's the same thing with our normal numbering system. It's 0 to 9, but it's 10 different possible values. So whatever your base is, you have 0 to 1 minus that base number. So we have, for us, it's 16, so 1 minus that is 15, so it's 0 to 15. Um, so yeah, this value, each digit is a factor of 16. So for example, we could go through like the first 3 digits. So we have digit 3, digit 2, and digit 1. So these are 16 to the 0. Actually, we'll do the first 4 that way. It's a little bit simpler. So this is 16 to the first, this is 16 to the 0, 16 to the second, 16 to the third. So just ignore this part, but yeah, so we always start with the 0th digit and then move up as we go along to the left. Now for octal, this is a base 8 value, as you can probably tell from oct. Um, yeah, so, oh, and also for hexadecimal, at times, if you're doing like programming languages and things of that nature, you will usually have the number written with 0x and then the number, just so people know that it's a hexadecimal number. So back to octal, this is a base of 8, so it's just 0 to 7. Those are our values, and for this is fairly self-explanatory uh, because it's less than 10. It's usually more difficult to conceptualize if you have a higher base than base 10. But even then, hexadecimal is really the only base above 10 that you'll commonly use. So that's why I'm just going over the ones that are actually common and the ones that are actually useful. So yeah, so this is 0 to 8, and then for the actual bases, we'll have digit 0, 0 to 8 to the 0. Then we have 8 to the first, 8 to the second, 8 to the third, and so on. So that's all you really need to know for octal. I haven't really come across it all that much. Usually I see hexadecimal and binary. And binary is the last one that we're going to go over right now. So for binary, you can either have a 0 or a 1. Those are your only two values that you can have. So because of that, this is like used, the most commonly used value, or the most commonly used base for digital systems, just because of how simple it is to use signals as either on or off. That's really how you dictate like most memory and signals and things of that nature. You notate them as actually either having a signal or not having a signal, and that's just translated easiest to a binary notation. So because of that, what you have is 2 to the 0, 2 to the first, 2 to the second, 2 to the third, and this translates to a 1, then a 2, then a 4, then an 8, and that will continue along. And as you practice with this, you'll start to understand and try to and over time you'll probably do it automatically. And the other thing to note, because right after this we're going to be doing some conversions, um, is that for every 4 binary digits, so so for every 4 binary digits, that is equivalent to 2 octal digits and four and 1 hexadecimal digit. Um, yeah, that's just because of the nature. They're all um, multiples of 2, so it's very easy to convert between them once you get the hang of it, just because of how similar they are. Because what you have here is, I can just go through an example. So um, I guess we'll just use this space here. Um, so what we have is, let me think for a second. So we could just use a 4-digit binary number. So we have 1, 0, 1, 1. This is the binary number. So this is base 2. And what we do here is, in order to convert it to octal, we can have values from 0 to 7, right? So what we have is, this is the um, this is 2 to the second right here. So we know that that's 4. So anything being multiplied here is a 4. So what we have is, I can actually go through the numbering system. So what you have is 0, which is all zeros. Then you have 1, which is just this digit. Then you have 1, 0, which is a 2. Then you have 1, 1, which is a 3. So right now in these 3 digits, we have we have 0 to 7. Actually, I was wrong earlier. Uh, I said the 2 digits equate to 1 octal digit, but it's actually 3. Sorry about that. Um, so what we have is, this area here is 0 to 7. So every 3 digits in binary is equivalent to 1 octal digit. So what we have here is 3 in octal for these 3 bits. Then what we have here is a 1, and since everything beyond that is a 0, we set this to a 1. So this is 13 base 8. Now, I guess we could do. I think it's easier to convert from binary to hexadecimal as well, so we're just gonna do it that way. Um, just because you need, I believe, another digit for octal, and I'm not super confident with my abilities with octal, so we're just gonna do this binary value 1011 to hexadecimal. So what we have is a 1101. So this is 0 to 15. So what we can do is add up all the bits and see how far up we are. So we have 3 here, and this is an 8, just because it's 2 to the 3. So 2 to the 3 times 1 is 8. So we have 8 plus 3, which is 11. So now you might be wondering which letter we use for 11. So you can, for now, you can just go through this area here and say 9, A is 10, B is 11. So this is equivalent to B with base 16. So that's sort of the general idea. We'll go over a couple more examples right after this. So let's do. So we're going to start off with a conversion from 250 to hexadecimal. So this is base 10. So the way we're going to do this is we have to think about it in terms of the hexadecimal digits. So what we want to find is the maximum value in hexadecimal that is equivalent to a value in decimal. So for example, we know 16 to the 0 is 1, 16 to the first is 16, 16 to the second. Let me actually pull out my calculator because I don't know this off the top of my head. Um, let's see. So 16 to the second is 256. Now I'm going to stop there because for the purposes of this problem we don't need to go any further, but you get the idea. You can go as far up as you need. So for 256, you know that that is less than 250. So these are all in base 10 right here. It's easy to think about these in terms of base 10 because we're so used to it. So what you do is 250 minus, actually, my mistake. We don't actually need 256. So um, what we're going to do is see how many times, so let's cross this out actually. So we're going to see how many times 16 is less than 250. So you have values from 0 to f, which is 0 to 15, that you have to look at. So you have to multiply values from 0 to 15 times 16 and see if you can find something less than 250. So you know that 16 times 16 is 256. So that's just barely above. So I'm going to try out and see if 1 times f is equivalent to something just under 250. So what we're going to do is see if 16 times f and see what that's equivalent to, and it should be less than 250. So we have 16 times 15 and we get 240. So we know that that's less than 250. So next what we do is 250 minus 240, and that is equivalent to 10. So now we have 10 left over, and we get our first binary, our first hexadecimal digit. So I'll write the answer over here. So we have F. F is the largest leftmost justified bit. Um, so we're just going to leave that there. And as we go along, we can add bits here. So now that we know that we're at 10, 10 is what we have left. So we have to subtract from 10. So we know that 16 is larger than 10, so we're not going to have another value of 16. And you really shouldn't, because everything at the 16th or at the 16 to the first place is already here. So that should be, if there's any overflow, that means that you screwed up earlier on, and that there should be a value at 16 to the second. So what we're going to do is check 16 to the 0 and see how many values are less than 10. And in this case, you just want it to be equivalent to 10. So what you have is minus a, and that is equivalent to 0. So what you have now is FA, and this is your final answer. Again, so if you get confused with how you're doing it, really the best thing that you can do is do more questions. So for the next one, we're going to be doing decimal to octal. So if you want to pause the video and uh, and do it for yourself and see if you can try it, and then start the video and again and see if you get the right answer. That's really up to you. So the next one is 100 octal or 100 decimal to octal. So what we have here is we're just going to do the same thing. 8 to the 0, 8 to the first, 8 to the second, and this is a 1, this is an 8, and this is a 64 because 8 squared is 64. And I don't think I need to go any further than this because you'll get like a ginormous number if you multiply 64 by 8 again. So we already know that 8 to the third is not going to come into play. So what we have is the digits 1 or 0, 1, and 2. So these are the three digits that we're dealing with and that we're trying to find values for. So what we're going to start off with is 8 to the second, which is 64. So we can do 100 minus 64, which is 36. So we know that it goes in only once, so we just put a 1 there because it's not, there's no multiple of 100 apart from 1, or sorry, there's no multiple of 16 apart from 1 that is less than 100. So from there we have 36. Now we have 36 and we have to subtract a multiple of 8 because 8 is less than 36. So what we have to think about is if you're fluent with your multiplication table, it's fairly simple for the conversions. You just have to think about it for a second. But I know 32 is 8 times 4, so we'll just get a 4 left over, and we get a 4 in our 8 to the first place. Then in the 0th place, because 4 is less than 8, we can just put the other 4. So our final answer is 144 with a base of 8. And I believe the next one is another 41 base 10 to binary. So what we're going to do now is same thing. I don't think I'm going to write out everything just because there would be a lot. But yeah, what you want to think about is a multiple of a squared value of 2, which is less than 41. So what you have is 2 to the, so actually I will write it out. So 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. We'll do those first. So we have 1, 2, 4, 8, 16. We're not there yet, so 2 to the fifth is equivalent to 32. And then 2 to the 6th is 64, so that's too big. So now we know since 32 is less than 41, that's the biggest value. We'll start with that place. So we have 5, 4, 3, 2, 1 different places that we have to deal with for this value. So because 32 only goes into 41 once, we have a 1 there. And really for this, you can't multiply it because it's only 0 and 1 are the values. So for binary, there's no point. You can't think about multiples for that. It just doesn't work that way because the only values are 0 and 1. So if it multiplies by 2, you probably missed a place over here, which is you just have to do something else uh, with your conversion. You just did it wrong. So now what you have in this place, so you subtract 41 by 32, and you get a 9. So now you have 9 left. So I know this, so it's 9 minus 8 is 1, so it's 2 to the third. Um, so what you have is a 1 here, and then you have 1 left, so just in the 1's place. So what you get is 1, 0, 1, 0, 1. So your final answer is 1, 0, 1, 0, 1. Yeah, so I think that you pretty much get the idea for converting from base 10 to one of the other bases. So what we're going to do now is, I believe I have 2 more examples, and that's going to be the end of the video. But the next 2 are going to be converting from different bases and not dealing with base 10. So right now we're going to be doing base 16 to binary. So this is actually very, very simple once you think about it. So I'm just going to do it this way. So we know that from what I said earlier, each digit in hexadecimal is equivalent to 4 digits in binary. So we're going to start with the least significant bit, which is the 0th bit, and then work our way up to the most significant bit, which is 4. So what we're going to do is 3, right? So the way we think about this is, I'll just write it out real quick. So 0, 0, 1, 1. So how do I know this? So the reason I know this is because for me, I've been doing this for a while, so I understand um, that this is just, this is the 0 and 1 is this bit. Then this controls 2. Then if you add 1, it's 3. So I think actually what I'll do um, really quickly is go over, I guess we could do 4 bits. I think that could be useful, just so you get a feel for how these digits increment. So what we'll do is, I guess we'll start here. We have 0, 0, 0, 0. So this is 0. Then we have 1. Then we have 2. Then we have 3. Then 4. Then we have 5, 6, 7, 8, 9, 10, 11. Oh, I think this is 12. Right? This is, or is that 15? Sorry, wait. Uh, 8, 9, 10, 11, 12. No, it's 12. Okay, so we have 12. Then we have, I'll just go up to 15. 13, 14, 15. So Yeah, so this is 0 to 15. Um, it's a little all over the place, but you get the idea. Um, yeah. So what you have is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is something that you'll get with time, but with practice, you know that this is 0 to 1 because it's the least significant bit. Then if you have nothing here, because this is the second place, this is 2 to the first, so this is a 2. Then if you add 1 to that, it's a 3. And that's sort of the idea as you go on and on and on. So that's just sort of something that you'll understand more as you practice more and get a better understanding for it. So I think um, that I'm just going to go through this as I normally would. So we have A, which is a 10. So what I know is this is an 8, right? Then we have 9 is if I have a 0 there, so, or if I have a 1 there, so if this is 1 more than 9, or this is 2 more than 8, this is a 10, because we know that this is 8, and this is a 2. So, because we know this is an 8 and this is a 2, so if we have both of them together, it is a 10. Next, we have 7. So, since this is the 8th place, we know that just under that is 0, 1, 1, 1. So this is 7. Then we have 4, which is also its own place. So we have 0, 1, 0, 0, because this is 2 squared, so that's 4. So now the final number is 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 0, 0, 1, 1. So it's also a similar deal when you're trying to convert back because this is 0 to 15. So what you do is group these in fours, and you have 3, then you have a 10, which is an A, then you have 7, and you have 4. So it is just um, a good way to think about it. That way it's easier to figure out how these conversions work. So the final thing that I'm going to be doing is hexadecimal to octal. I shied away from it earlier just because I'm not super confident with it, but um, I mean, I think we'll be able to figure it out. It's probably fine. So the way that I would do this is actually convert it to binary first, because that's simplest. So we actually have the value from the earlier problem. So anytime you're converting from hexadecimal to octal, in my opinion, it makes more sense to convert to binary than octal, just because it's simpler to think about it that way, because otherwise you have to try and convert bases of 16 um, to maybe decimal, then convert it back to octal, and it's easier to group it in binary. So we're going to do a similar thing to what we did earlier. So the value that we have from the previous slide is 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 0, 0, 1, 1. Okay? Now, the grouping system for octal is what's different. With hexadecimal, it's groups of 4. Octal is groups of 3. So you do this. Okay. So with here, we have a 3. Then we have a 4. Then we have a 6. Then we have a 3. And we have another 4. So our final value is 4, 3, 6, 4, 3. This is a base 8. So yeah, that's going to be the last thing I do in this video. I hope you enjoyed. I definitely think that this is a good foundation for digital systems, and it's going to come up a lot, especially if you work at all in like assembly, in like with registers and things of that nature. And then definitely if you're like electrical engineering, when you're designing systems of that nature, it's very useful to understand. And even if you're just comp sci, it's useful to get a foundation in these basic number systems. Just conceptually to think about things, it's a lot easier if you have a foundation with this. So yeah, I think in the next video I'll probably go over. Um, Let me see. I think I had mentioned what I want to go over. Probably two's complement, one's complement is something that I want to go over, and then maybe Boolean algebra. And if we have time, we'll probably also do logic gates, but I think that might end up being the third video in the series. So yeah, if you liked the video, please let me know in the comments. Um, yeah, so I'll probably be doing this for a while. All right, bye.